Now I introduce a Kalman filter. Kalman filter is a predictor and a corrector type of estimator. In the ideal case, without noise, a linear quadratic regulator can be used to find a sequence of controls that user to generate the optimal trajectory. However, if dynamic, it means process noise for the dynamic, and also a noise for the measurement involved in the dynamic system, we cannot get the true trajectory or optimal trajectory. So right, so in this case, Kalman filter is used to generate a more accurate trajectory based on the noise, the dynamic process error and the measurement noise. Let's say we start from state x k minus 1. We have this control and we have this so-called process noise. If we use the system dynamic, we will go to the next state is here. And we measure what's the next point is here. Actually, the true next state is here, is xk. The Kalman filter is combine this predict next state and the measured state, because both of them have a noise. So we use this measurement to modify this predict next state, push this next state closer to the true state. This is the result generated by the Kalman filter. It's more closer to the true state than predict next state and measure the state. That's the idea of the Kalman filter. Here, the Z is this measurement. This X is the true next state. And we define this prior next state. We calculate the posterior next state. Once we have this prior next state and posterior next state, we define two errors. One is the true next state minus the prior next state. One is the error for next true state minus next prior posterior state. Based on these two errors, we define two covariance. This one is from this prior error, one is the posterior error. Kalman filter try to find the posterior next state from a prior next state and from the measurement. From this dynamic system dynamic, you can see this posterior next state based on the prior next state and modification by Kalman filter. So right now the main problem is how can we find this case called Kalman gain. To calculate Kalman gain, we minimize this covariance and solve for the we call Riccati equation for K. We got this case formulation. Because the right hand in the right hand, all the variables are known, so we can update this common gain. Once we get this common gain, we can from this system dynamic, we will know what's the best next state. So these are two special cases. One is if no measurement noise. No measurement noise, that means this R close to 10 to 0. So the next posterior state is divided by this measurement. And if we don't have the process noise, that means this pk to 0, and we can see the next state determined by the previous or prior next state. So let's get a summary. As we said before, Kalman filter is a predictor and predictor character estimator. Here is his update. First, we calculate the prior next state based on the previous estimate state by Kalman filter. And then from the error defined by this prior next state, we calculate this P. Once we got this this prior next state and the P minus, then we start the correction step. The correction step, first we calculate the common gain. From a common gain, we get the estimate next state. This state is better than the previous state, or also better than the measurement. After we got this estimate next state, then we update. We got to update this P. Use this P, and then we calculate this. Predict this to this X next prior state and P prime, and use these two variables or to correct the previous next state to get a more accurate estimate next state X hat. That's the whole idea about the Kalman filter. For more details, please check with these references. Thank you. Bye.